In this video, we're going to look at how to do a linear programming example. There's a lot of different parts to this, so I'll make sure that in the description it's kind of broken down into the different parts we have to figure out. But let's look at our situation. So Jack and Jill have a bakery. They make two different kinds of cookies. They've got plain cookies and iced cookies. So they sell them a full box. They don't do one at a time. It's just one box of plain or iced cookies. They obviously want to try to sell all the cookies that they make. So we have to identify what our variables are going to represent. Well, in this case, we have to think about what don't we know? What's the number that could change depending on other variables? Well, we're only selling boxes of plain cookies and iced cookies, and each day could be different. How many boxes of plain cookies they sell and how many boxes of iced cookies they sell. So those are going to be our two variables for x and y. I'm just going to go in order, so I'll have plain go with x and iced go with y. And I don't want to just say plain and iced. Right? That doesn't really give me a lot of context. I have an idea of what's going on, but if someone else were to look at it, it could be confusing. So I need to be more specific, and my variables need to represent the number of something. So I always want to put number of and then the item that my variable represents. So the number of, and it's not just plain cookies, but it's boxes of plain cookies. So in the back of my mind, I'm just thinking plain and iced, but this is the full representation of our variable x, and for y, it's the number of boxes of iced cookies. Okay, so now that we've established what x and y represent, now we need to look at what are our constraints, our limitations. Okay. So in this case, we've got three constraints. And so we need to take a look at these, write out an inequality for each, and that's going to help us determine the most efficient way to utilize our materials and be able to sell the most boxes of cookies. So plain cookies require 1.2 pounds of cookie dough. Iced cookies are 0.9 pounds of cookie dough. And Jack and Jill have 72 pounds of cookie dough to work with. Notice how each of those numbers have to deal with cookie dough. So each constraint has to have the same category. So all the numbers in one inequality or constraint deal with the same label. So in this case, it's pounds of cookie dough. The second one, plain cookies require no icing. Box of iced cookies require 0.4 pounds of icing, and they have 20 pounds of icing total. So again, this constraint all has to do with pounds of icing. Our third constraint is how long it takes to make the cookies. So plain cookies for one box requires 0.1 hour to prepare. Iced cookies, 0.15 hours to prepare. And they have 9 hours to work on their cookies each day. So let's go ahead and write out the inequalities for our three constraints. So the first one, again, is based on pounds of cookie dough available. So there's 1.2 pounds for plain cookies, 0.9 for iced cookies, and 72 total. So one way to look at this is to kind of write out your numbers and then piece together where your variables are and your inequalities. So we know that x represents the number of boxes of plain cookies. That goes with 1.2, right? So plain cookies goes with 1.2. The iced cookies go with 0.9, so it's 0.9y. And then this 72, that's our total. Anytime we've got that total there, that goes on the end. So that's going to be on one side of our inequality by itself. And the amount of plain cookies, or cookie dough for plain cookies and cookie dough for iced cookies together are going to be, and then we got to figure out the inequality. It's going to be less than or equal to 72. We don't have more than 72 pounds to work with, so this amount right here can't be more than 72. It can be less than. Obviously, Jack and Jill would like to use all 72 if that's the most efficient way to do it. So it could be equal to, but can't be more than. So there's our inequality for that first one. All right, we'll go a little quicker for the second one here. This is icing. Well, plain cookies have no icing, so that's like 0x. All right, we don't really need to write out the 0x, so we'll erase that. But iced cookies have 0.4 pounds, and that goes with y because that's iced. And there's 20 pounds total to deal with. Again, we can't use more than 20 pounds because that's all we have. So less than or equal to, again, for this inequality. So I'm just kind of like matching what I wrote out for the first one. And now my third one, this is based on the number of hours Jack and Jill have to work on the cookies. Plain is 0.1 hours. And then iced cookies is 0.15. Right? And together, they can't spend more than 9 hours, so less than or equal to. So there are our three constraints for our problem. Copy and paste all this. So now we want to go ahead and graph. Ooh, nope. Okay. So I'm just going to have to rewrite it here. So we had 1.2x plus 0.9y is less than or equal to 72. We had 0.4y is less than or equal to 20. And then we had 0.1x plus 0.15y is less than or equal to 9. So now we need to graph these so we can start to get a better sense of how we can maximize our profit. All right. So once we graph them all, we're going to shade and figure out where the shading overlaps, and that's going to be our feasible region or our solution. So that's all the different possible combinations where we're not using more materials or working more hours than we have available. So I've got a graph here that's already labeled. I need to figure out my intercepts for each of my inequalities, and then I'm going to graph the intercepts and just connect that because I know each of these are a linear function. So my first example, I'm going to take, I'm going to figure out my x and my y intercept here. So for my x-intercept, if y is 0 here, then I basically just cover up my y term. And now I solve for x. So I assume that there's an equal sign, and I just say if 1.2x equals 72, what would x be equal to? So that ends up being 60. So my x-intercept there is 60. And then my y-intercept, my x value is 0, so I basically cover up my x term. And now I solve for y, so 0.9y equals 72. And I get a y value of 80. Get rid of that. 80. Okay, so I've got my x and my y-intercept. So I can plot my x-intercept down there at 60, my y-intercept up here at 80, and I'm going to try to be accurate here and draw an exactly straight line. That's not even exact, but close enough. Okay, so now for my second inequality, 0.4y is less than or equal to 20. Well, I don't have an x term there. So this tells me that it's going to be either a horizontal or a vertical line. So again, I solve as if it was 0.4y equals 20, and I get y equals 50. And so if it's y equals 50, then that means every point on that line has a y value of 50, which means it's a horizontal line right here at 50. So again, I'll take a straight line here, and I just go straight across there. Now, my third inequality, same thing. I want to find my x and y intercept. So my x-intercept, cover up the y value, solve for x, and we get 90. And for my y-intercept, cover up the x value, solve for y, and we get 60. So x-intercept of 90, y-intercept of 60. Draw my line. Okay. I'm just going to adjust that a tad. Okay, so there are our three lines for our three inequalities. Now, normally we have to think about if it needs to be a solid or a dashed line because we're dealing with inequalities, but they're all less than or equal to, so I know they can all be solid lines. Also remember that the x and y axis are given constraints in a linear program example because we are only dealing with positive numbers, right? We can't have negative hours worked or negative icing used. So everything is in quadrant 1, positive x and y values. So technically we've got 5 constraints in here, and all of these inequalities are less than. So they're all going to be below, and I don't want to shade for 5 different lines, so I'm going to look at where all the overlapping shading would be to figure out my feasible region. And that's going to be right, it's not working. So my shaded region is going to be right in here, so it's above my x and y axis, but below all 3 of my lines here. Okay, and now I got to look at where are my intersecting points for all these lines. So if I go, this is one of my vertices. Here's another here, 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 and here. So I've got technically 5 vertices, and I want to figure out which one of those are going to help maximize my objective function, which is to make the most money. Okay, so I don't have quite enough time to finish on this video, so I will add a second video where we wrap up looking at these vertices. We talk about what the objective function is, we write that equation, and then we use these vertices to figure out which one helps Jack and Jill maximize their profit.